Hi everyone, my name is Jack Gabriel. I'm a senior physics and math major at Rollins College down in Orlando, Florida, and today I'm going to be talking with you all about nuclear fusion and its promise of nearly limitless clean energy. So, with that being said, let's begin. Over the past couple of decades, climate change has been an increasing source of concern. This problem will only continue to grow in the coming years as the world's energy usage continues to increase unless cleaner sources of energy are employed. A common proposal to decarbonize the current system would be to phase out fossil fuels in favor of moving to 100% renewable energy sources. While these sources will undoubtedly be important for the future decarbonized energy system, there are reasons why relying solely on these sources would be problematic that will not be discussed in this video. Instead, I will focus on the one source that has the promise of nearly unlimited energy with next to zero emissions, nuclear fusion. As opposed to nuclear fission, where a radioactive uranium nucleus is split apart, in fusion, two non-radioactive hydrogen nuclei are combined, releasing massive amounts of energy in the process. For example, the hydrogen in 1 liter of water through fusion would provide the same amount of energy as 260 liters of gasoline, with none of the emissions. So, if fusion is so great, why isn't it being used today? While the potential payoff is huge, nuclear fusion is difficult to accomplish efficiently. Remember, the goal is to bring two positive charges close enough together, within a few femtometers, so they fuse together. As anyone who has tried to bring the wrong ends of magnets within a few millimeters together knows, it's tough to do. Now, the way to overcome this problem is to make the system very hot, so that the charges are moving fast enough that they end up colliding and fusing together. And when I say hot, I mean hundreds of millions of degrees Celsius hot. So the problem becomes how to contain this hot soup of charges known as a plasma. In space, stars, such as our sun, use the gravitational potential energy from their immense mass to contain the hot plasma. On Earth, this is not possible. And there have been two very different approaches to achieving nuclear fusion. Use the plasma's own inertia, or use magnets. Inertia is the resistance of a physical body to change its velocity. So, for inertial confinement fusion, the guiding principle then is that if a bunch of laser beams are shot at a sphere of hydrogen, the plasma's inertia will cause for it not to instantly rapidly expand. During this time, the laser can cause for the sphere to implode, which will lead to the hydrogen fusing together. Having the laser beams directly incident on the sphere is known as direct drive inertial confinement fusion, but there is also indirect drive, which is more commonly used, where the laser beams irradiate a gold cavity known as a hohlraum, which then produce X-rays that implode the sphere. While it sounds more complicated, the X-rays are able to more uniformly compress the sphere, which is very important to achieving nuclear fusion. The biggest problem with inertial confinement fusion is the large number of instabilities that inhibit it from achieving fusion. For instance, if the sphere is not perfectly compressed uniformly, then it can break apart, leading to catastrophic failure of the shot. This graphic is another case of this, known as the Rayleigh-Taylor instability, which can be seen when oil is placed on top of water, as an example. So, while inertial confinement fusion is an interesting and novel approach to achieving nuclear fusion, a lot more research is necessary before it will be viable as a source of clean energy. This brings me to the other type of confinement scheme, magnetic confinement fusion. Since the plasma is made up of charged particles, it can be confined by a magnetic field. The simplest way to achieve this is through the use of a cylindrical configuration. The issue here is with the losses suffered at both ends. These losses can be mitigated by curving the magnetic field into itself, creating a torus. This purely toroidal magnetic field is also problematic as well because it is stronger on the inner radius than it is on the outer radius. This can be overcome through the addition of a poloidal magnetic field that causes for the charges to, as they move around the torus, They also move in a circle, yielding a net helical motion. In a tokamak, as pictured, this is accomplished through the use of a transformer and poloidal coils, which cause for its operation to be inherently pulsed. Now, there also exists another type of device, known as the stellarator, where the same type of helical motion is achieved through the use of a more complicated design and some really difficult physics. With the stellarator, however, steady-state operation is possible. Both of these devices are being used to prepare for the completion of ITER, the International Thermonuclear Experimental Reactor pictured here, which is a massive tokamak. To give you an idea as to just how huge this machine is, boxed in red is a person. Scheduled to be completed this decade, ITER has just one goal: to prove that net energy gain from nuclear fusion is possible. And, according to all the models and predictions, that is exactly what it will achieve. The next step then, demo, will be to improve upon ITER to create an operatable, steady-state fusion power plant. To finish, there's an old adage that nuclear fusion is 20 years away and always will be. Well, it's quite poetic. ITER in Latin means the way, and this machine will both put to rest that old adage and showcase humanity's pathway towards a greener future. Thank you.